Well, I forgot to log into my workstation here. Give me 1 second. I didn't even notice that it locked. Okay. Alrighty. So yesterday I wrote a bunch of programs, mainly using threaded approaches. Um, this morning, what I wanted to do is get through the reading and then move on to writing more, I guess you would say, multiplexed solutions. So instead of having an unlimited amount of threads being created for every connection, having a bounded set of threads, ideally, the equivalent to the number of cores that are on the machine, and having those threads multiplexing their I/O operations. And then having some type of mechanism for testing workloads. Because the test that I have right now, the server can block on command a specific file descriptor. It can unblock it. It can emit a write to it. It's very, very limited. What would be more realistic is having a server that, let me move this camera so it's actually pointed at me. Having a server that does some amount of I/O, so I/O heavy workloads, CPU heavy workloads, and then workloads that are just blocked on dependencies, and that can be simulated, with something like sleep, because like in a normal, in production environment in a distributed system, you'll have a bunch of different types of workloads. Some of them can be easily serviced just with a little tiny bit of I/O. Some of them take a lot of I/O. Some of them take some CPU time. Some of them take very little CPU time. Some of them are blocked on dependencies, like upstream database servers and stuff. So, yeah, given that diversity of workloads, I would like to have like a benchmark that can benchmark different solutions, so you can see which ones are better than others. So yeah, let's go ahead and get the reading done this morning. Also, at some point, I'd like to look into libevent and libuv, or libuvs, I should say. Let's go to chapter 63. Jobs. Yeah, this is where I have my jobs around. So I'm going to kill these other terminals, and we're going to go into to-do. We'll say experiment with lib event, which is mentioned in the book, and then also with libuv. I don't even know if I want to do these. Implement a multiplexed event IO server. Evented IO server. Async IO server with IO uring. These are all things I want to do with epoll. We'll say develop a realistic testing benchmark. Yeah. Okay. I think that's some things that I want to do as part of this chapter. Let's do make clean. And I can close these out now that I have them as to do. Every morning I'm just like sneezing, congested. Okay. Alright, so we got through that. Which technique? We already got through that. Here we go. Level triggered and edge triggered notification. Before discussing the various alternative I/O mechanisms in detail, we need to distinguish two models of readiness notification for a file descriptor. Level triggered notification and edge triggered notification. Level triggered notification is a file descriptor is considered to be ready if it is possible to perform an I/O system call without blocking. Okay, that's what I assumed everything was. So what's edge triggered? Edge triggered notification. Notification is provided if there is I/O activity, e.g. new input on a file descriptor since it was last monitored. So that could be that the I/O will actually block. I/O operation will block, but it's less likely to block. So really, I mean, level triggered is what we would want, right? I guess ePOL can do edge triggered and signal driven I/O is edge triggered. Table 63.1 summarizes the notification models employed by I/O multiplexing. Signal driven I/O and ePOL. The ePOL API differs from the other two I/O models in that it can employ both level triggered notification, the default, and edge triggered notification. Details of the difference between these two notification models will become clearer during the course of this chapter. For now, we establish how the choice of notification model affects the way we design a program. When we employ level triggered notification, we can check the readiness of a file descriptor at any time. This means that when we determine that a file descriptor is ready, e.g. it has input available, we can perform some I/O on the descriptor and then repeat the monitoring operation to check if the descriptor is still ready, e.g. it still has more input available, in which case we can perform more I/O and so on. In other words, because the level triggered model allows us to repeat the I/O monitoring operation at any time, it is not necessary to perform as much I/O as possible, e.g. read as many bytes as possible on the file descriptor, or even perform any I/O at all, each time we are notified that a file descriptor is ready. By contrast, when we employ edge triggered notification, we receive notification only when I/O events occur. We don't receive any further notification until another I/O event occurs. Furthermore, when an I/O event is notified for a file descriptor, we usually don't know how much I/O is possible, e.g. how many bytes are available for reading. Therefore, programs that employ edge triggered notification are usually designed according to the following rules. After notification of an I/O event, the program should, at some point, perform as much I/O as possible, e.g. read as many bytes as possible, on its corresponding file descriptor. If a program fails to do this, then it might miss the opportunity to perform some I/O, because it would not be aware of the need to operate on the file descriptor until another I/O event occurred. This could lead to spurious data loss or blockages in a program. We said at some point because sometimes it may not be desirable to perform all the I/O immediately after we determine the file descriptor is ready. The problem is that we may starve other file descriptors of attention if we perform a large amount of I/O on one descriptor. We consider this point in more detail when we describe the edge-triggered notification model for ePOL in section 63.4.6. If the program employs a loop to perform as much I/O as possible on the file descriptor, and a descriptor is marked as blocking, then eventually the I/O system call will block, when no more I/O is possible. For this reason, each monitored file descriptor is normally placed in non-blocking mode, and after notification of an I/O event, I/O operations are performed repeatedly until the relevant system call, e.g. read or write, fails with an error E again or E would block. Employ non-blocking I/O and with alternative I/O models. I guess something that just occurred to me. Name of I/O U-ring library. What is it saying? Lib U-ring. Okay, so employing non-blocking I/O with alternative I/O models. Non-blocking I/O, the O non-block flag, is often used in conjunction with the I/O models described in this chapter. Some examples of why this can be useful are the following. As explained in the previous section, non-blocking I/O is usually employed in conjunction with I/O models that provide edge trigger notification of I/O events. If multiple processes or threads are performing I/O on the same open file descriptors, then from a particular process's point of view, a descriptor's readiness may change between the time the descriptor was notified as being ready and the time of subsequent I/O call. Consequently, let me reread that. My mind was wandering a little bit. If multiple processes or threads are performing I/O, let me turn this light on, a little bit more light. Actually, that doesn't really help. What I really want is like a better light on the text as I'm reading. It doesn't cast a shadow. I do have a couple lights that might help. Let me see if I can find one. Be right back. There we go. I got like a huge extension cord from my basement and use that to wire up this light here, which is a little bit overkill, but just really don't want to spend much time on optimizing the solution there. All right. Where did we leave off? We were reading about employing non-blocking. Let's read from this second bullet part here. If multiple processes or threads are performing I/O on the same open file descriptors, then from a particular process point of view, a descriptor's readiness may change between the time the descriptor is notified as being ready and the time of the subsequent I/O call. Consequently, a blocking I/O call could block, thus preventing the process from monitoring other file descriptors. This can occur for all of the I/O models that we describe in this chapter, regardless of whether they employ level-triggered or edge-triggered notifications. Even after a level-triggered API such as select or pull informs us that file descriptor for a stream socket is ready for writing, if we write a large enough block of data in a single write or send, hold on, let me read that. Even if a level-triggered API such as select or pull informs us that a file descriptor for a stream socket is ready for writing, if we write large enough block of data in a single write or send, then the call will nevertheless block. Makes sense? If in rare cases, level-triggered APIs such as select and pull can return spurious readiness notifications. They can falsely inform us that a file descriptor is ready. This could be caused by a kernel bug or be expected behavior in an uncommon scenario. Section 16.6 of Stevens et al. 2004 describes one example of spurious readiness notifications on BSD systems for a listening socket. If a client connects to a server's listening socket and then resets the connection, a select performed by the server between these two events will indicate the listening socket as being readable, but a subsequent accept that is performed after the client's reset will block. So basically, like, you set your socket into non-blocking mode because you're using these traditional read and write style syscalls that can block if non-block is not provided. And you don't want to block because you got to move on to the next guy who might be needed to do some I/O. You don't want to be blocked. So non-blocking is a critical feature of the legacy, like I should say traditional I/O syscalls that should be enabled when you're using select, pull, epull, KQ, stuff like that. Otherwise, you might block and freeze the whole thing. I/O multiplexing. So it's interesting is like this is not big enough to see the entire page, so I'm going to have to zoom out here. There we go. I/O multiplexing allows us to simultaneously monitor multiple file descriptors to see if I/O is possible on any of them. We can perform I/O multiplexing using either of the two system calls with essentially the same functionality. The first of these, select, appeared along with the sockets API in BSD. This was historically the more widespread of the two system calls. The other system called pull appeared in System V. Both select and pull are nowadays required by SysV3. Select, I imagine it operates similar to the select and go. We can use select and pull to monitor file descriptors or regular files for regular files, terminals, pseudo-terminals, pipes, FIFO sockets, and some type of character devices. Both system calls allow a process either to block indefinitely, waiting for file descriptors to become ready, or a specified time, or to specify a timeout on the call. Sorry, I wasn't paying attention when I read that. Both system calls allow a process to either block indefinitely, waiting for file descriptors to become ready, or to specify a timeout on the call. Okay, that makes sense. In Go, select blocks by default, and then you can have like a timer, the time.after channel thing that will allow the select a timeout. So we call select. We got number of file descriptors. We have a file descriptor set for the read and the write. Accept. I'm not sure what accept is. And then we have this time val for the timeout. The end FDs, read FDs, write FDs, and accept FD arguments specify the file descriptors that select is to monitor. The timeout argument can be used to set an upper limit on the time for which select will block. We describe each of these arguments in detail below. I imagine the integer is the ready file descriptor. Oh no, it's a number of ready file descriptors. So maybe it writes its value into the accept FDs about what is ready. Not sure. In the prototype for select shown above, we include systime because that was the header specified in SysV2. On some Unix implementations require this header. Systime header is present on Linux, including it does no harm. File descriptor sets. It's amazing how much effort has gone into making programs portable, more easily portable between operating systems. Like compatibility, portability of source code itself. It is amazing. What also is amazing is that like there's this implicit idea that like when you're compiling on a machine, the machine that you're compiling on is the target. Because like in my mind, if you're distributing binaries, then portability is whatever libraries you're dynamically linking against and the syscall interface. And binaries aren't portable across operating systems anyways. It's just yeah. Most projects build binaries for distribution that target the different operating systems and architectures that they target. So really all its portability is for people who want to be able to build on multiple different systems instead of having just like a really good cross compiler that can target all these different operating systems. Yeah, I mean, in my mind, like the source code should build in this hermetic environment, and it should produce artifacts that can then be executed on any of the targets that you are targeting. So single source, single build environment, consistent build environment, outputs multiple artifacts for the target systems. But I think the way that this model was initially conceived is that source code was the unit of distribution. And you distribute it to all your targets, and then you compile on the targets. In which case, you need source code portability instead of just having a source code that can then cross-compile and target multiple operating systems. I'm like grappling with this because my mentality coming from Go is like, because cross compilation is so easy, like why would you ever care about whether the target machine has a specific header file? Like in Go, also most of the time in Go you're compiling static binaries, so literally the interface that you're targeting is this operating system syscall table. So it's architecture and syscall table that you're like depending on. So like, why would you care at all about what header files are available on the target machine? And I think that's the difference. All right, file descriptor sets. The read FDs and write FDs and accept FDs arguments are pointers to file descriptor sets represented using the data type FD set. These arguments are used as follows. Read is the set of file descriptors to be tested to see if input is possible. Input is possible. If reads are possible, Write is a set of file descriptors to test to see if output is possible. And accept is a set of file descriptors to test to see if an exceptional condition has occurred. Okay. So where does it write the file descriptors that are ready? Because it returns the number of ready file descriptors. But like, where does it put those? The term exceptional condition is often misunderstood to mean that some sort of error condition has arisen on a file descriptor. This is not the case. An exceptional condition occurs in only a few cases on Linux, including the following. A state change occurs on a pseudo-terminal slave connected to a master that is in packet mode. Out-of-band data is received on a stream socket. Typically, the FD set data type is limited as a bit mask. Typically the FD set data type is implemented as a bit mask. However, we don't need to know the details since all manipulation of file descriptor sets is done via the macros fd0, fd set, fd clear, fd is set. Okay. These macros operate as follows. 0 initializes the set pointed to by fd set to be empty. Set adds a file descriptor fd to the set pointed to by fd set. Clear removes the file descriptor fd from the set pointed to by fd set. Is set returns true if the file descriptor fd is a member of the set pointed to by fd set. A file descriptor set has a maximum size defined by the constant fd set size. On Linux, this constant has a value of 1024. Other Unix implementations have similar values for this limit. Even though the fd star macros are operating on user space data structures, and the kernel implementation of select can handle descriptor sets with larger sizes, glibc provides no simple way of modifying the definition of fd set size. If we want to change this limit, we must modify the definition in the glibc header files. However, for reasons that we describe later in this chapter, if we need to monitor large numbers of descriptors, then using epoll is probably preferable to use of select. The read FDs, write FDs, and accept FDs arguments are all value result. Before the call to select, the FD set structure pointed to by these arguments must be initialized to contain a set of file descriptors of interest. The select call modifies each of these structures so that on return, they contain the set of file descriptors that are ready. Since these structures are modified by the call, we must ensure that we reinitialize them if we are repeatedly calling select from within a loop. The structures can then be examined using isSet. If we are not interested in a particular class of events, then the corresponding FD set argument can be specified as null. We say more about the precise meaning of each of these three event types in section 63.2.3. So you give it the sets, and then it modifies the sets. It's a bit of a weird interface, but sure. The nFD's argument must be set to 1 greater than the highest file descriptor number included in any of the 3 file descriptor sets. This argument allows select to be more efficient, since the kernel then knows not to check whether a file descriptor number higher than this value are part of each file descriptor set. Okay. Timeout argument. The timeout argument controls the blocking behavior of select. It can be specified either as null, in which case select blocks indefinitely, or as a pointer to a time value structure. If both fields of timeout are 0, then select doesn't block. It simply polls these selected file descriptors to see which ones are ready and returns immediately. Otherwise, timeout specifies an upper limit on the time for which select is to wait. Although the time value structure affords microsecond precision, the accuracy of the call is limited by the granularity of the software clock. SUSY3 specifies that the timeout is rounded upward if it is not an exact multiple of this granularity. SUSY3 requires that the maximum permissible timeout interval be at least 31 days. Most Unix implementations allow a considerably higher limit since Linux x86-32 uses a 32-bit integer for time t-type. The upper limit is many years. When timeout is null, I wonder if I can get this down off my head a little bit. Can I just move this like that? But I have to extend it like that. There we go. Ah, look at that. Just to get it out of my eyes. It is very bright though, so maybe I'll dial it down a little bit. I think that'll be good. And it's out of the camera too. That's good. Do want it to be a little bit higher though. There we go. Maybe do one more up. That. There we go. Hope that's in the camera. Whatever. Wonder if I could just move the camera. There we go. Alright. When timeout is null or points to a structure containing non-zero fields, select blocks until one of the following occurs. At least one of the file descriptors specified in read, write, or accept becomes ready. The call is interrupted by a signal handler, or the amount of time specified by timeout has passed. In older Unix implementations that lacked a sleep call with a sub-second precision, nanosleep, select was used to emulate this functionality by specifying NFDs as 0, and then the sets as null, and the desired sleep interval is in timeout. Okay. On Linux, if select returns because one or more file descriptors became ready, and if timeout was not null, then select updates the structure to which timeout points to. I gotta reread that. Alright. You know what? I think I'm gonna just go to the washroom real quick and splash some water on my face because I am not fully awake right now. So I'll be right back. I still feel kind of like groggy. I didn't really sleep well last night. I got under 7, like slightly under 7 hours of sleep. I was up late, so I think I might be a little bit slow this morning. All right, so let's continue reading. On Linux, if select returns because one or more file descriptors became ready, and if timeout was not null, then select updates the structure to which timeout points to indicate how much time remained until the call would have timed out. However, this behavior is implementation specific. Substitute 3 also allows the possibility that an implementation leaves the structure pointed to by timeout unchanged. In most other Unix implementations don't modify this structure. Portable applications that employ select within a loop should always ensure that the structure pointed to by timeout is initialized before each select call and should ignore the information returned in the structure after the call. So it's like a Linux specific feature if you want to like see how much time you would have had to wait to timeout. I can imagine that might be helpful in some situation. Substitute 3 states that the structure pointed to by timeout may be modified only on a successful return from select. However, on Linux, if select is interrupted by a signal handler so that it fails with the EENTER, then the structure is modified to indicate the time remaining until a timeout would have occurred, like a successful return. That's helpful because if you get interrupted by the signal handler, you can just, redo the select call and specify the timeout as the same value because it's modified to be a lower value than what you initially set it to. Okay, next page. If we use the Linux-specific personality system call to set a personality that includes the sticky timeouts personality bit, then select doesn't modify the structure pointed to by timeout. I think this might be the first time they've mentioned personalities in the book. Let me look up. Let's see. Personality. Yeah, 1 through 3, 4. This is the only time they mention personality. Really? That's crazy. Okay. I'm just going to take a little bit of a side tangent here because I ran into personalities when I was learning about IOUing, because I believe they have their own concept of personalities that are separate from personalities in the Linux security modules. What are personalities in Linux? And if we do a man to personality, set the process execution domain. Linux supports different execution domains or personalities for each process. Among other things, execution domains tell Linux how to map signal handlers to signal actions. The execution domain system allows Linux to provide limited support for binaries compiled under other Unix-like operating systems. Okay. So this isn't a security feature, this is a compatibility feature. If persona is not all Fs, then personality sets the caller's execution domain to the value specified by a persona. Specifying persona as all F provides a way of retrieving the current persona without changing it. A list of available execution domains can be found in personality.h. The execution domain is a 32-bit value in which the top 3 bytes are set aside for flags that cause the kernel to modify the behavior of certain system calls so as to emulate historical or architectural quirks. The least significant byte of a value defining the personality the kernel should assume. The flag values are as follows. So you call personality from within the process. It's a syscall. And it changes its personality. So further syscalls would have different behavior. Bunch of different personalities. SunOS. What is sticky timeouts? Seems like sticky timeouts is a common thing because they mention it in the book here, and it's mentioned in the man page a lot. Apply sticky timeouts. Let's do man sticky timeouts. Nope. Okay, let's do the AI summary here. Linux personality is usually referred to execution domain personality of the process, a kernel feature that slightly changes how a program behaves so Linux can emulate quirks of other Unix-like systems. This is controlled by the personality system call. What are sticky timeouts? Sticky timeouts isn't a formal kernel term with a single universal definition. It's a phrase that shows up in Linux networking discussions to describe timeouts that persist or stick to an object or state instead of being reset each time activity happens. Exact meaning depends on the context. Here are two main ways it's used. A timeout that applies to a whole operation session, not per individual read-write attempt. Each read, receive, select, etc. gets a fresh timeout. If partial progress happens, the next call gets the full timeout again. Okay. Sticky timeout, deadline style. Timeout starts once. Time already spent waiting counts against the total. Even if the data arrives, the remaining time keeps shrinking. Okay. So up here, he said, if we're using Linux-specific personality system call to set the personality that includes the sticky timeout personality bit, then select doesn't modify the structure pointed to by timeout. Makes sense. All right, return value from select. As its function result, select returns one of the following. A return value of -1 indicates that an error occurred. Possible errors include bad F and enter. Bad F indicates that one of the file descriptors in read fs, write fs, or accept fts, is invalid, e.g. not currently open. Enter indicates that the call was interrupted by a signal handler. As noted in section 21.5, select is never automatically restarted if interrupted by a signal handler. Okay. A return value of 0 means that the call timed out before any file descriptor became ready. In this case, each of the return file descriptor sets will be empty. Positive return value indicates that one or more file descriptors is ready. The return value is a number of ready descriptors. In this case, each of the return file descriptor sets must be examined using fd_is_set in order to find out which IO events occurred. If the same file descriptor is specified in more than one read FDs, write FDs, and accept FDs, it is counted multiple times if it is ready for more than one event. In other words, select returns the total number of file descriptors marked as ready in all three return sets. Example program. The program in listing 63.1 demonstrates the use of select. Using command line arguments, we can specify the timeout of the file descriptors that we wish to monitor. The first command line argument specifies timeout for select. The second, a hyphen, is specified here. Then select is called with the timeout of null, meaning block indefinitely. Each of the remaining command line arguments specifies the number of file descriptors to be monitored, followed by letters indicating the operations of which a descriptor is to be checked. The letters we can supply here are R, ready for read, and W, ready for write. So, that's a usage error, so the usage is timeout or dash, and then we say fd num, and then the options to read and write. For example, so that's blocking 0 read write 1 write. I wonder if that's existing file descriptor numbers. I guess we'll find out in the implementation. Okay, how many pages is this implementation? It's a little over a page. So this thing figures out the timeout, whereas PTO is a process timeout, something. Could be null, or it could be timeout in seconds. NFDs is 0. So we have except is going to be null. Where's our select call? Here, it's down here. So except is null. So initialize our read and write file descriptor sets as 0. And then we go over our argc. We skip over the 0th element, which is our command, our 1th element, which is the timeout. We go from there. We then scanf to pull out our file descriptor number and whether it's read and write. So that'll give us FD here. If it's not equal to, then we have an error. Okay. I said it's the maximum NFT. Okay, that makes sense. And then we set it into the read and write if stircher. What is stircher? Man stircher. Stircher function returns a pointer to the first occurrence of the character C in the string. So if it's not null, then it exists in the string, in which case we set it in the appropriate set. Okay. So then we call select, get back the ready. The ready can be ported here if it's not -1. And then we go over all the file descriptors that are less than the NFDs. And we say, hey, your file descriptor. So this is the part where we have to like iterate over everything. So ready would be the number. So we're iterating over all the file descriptors up to NFDs, which is the max numbered file descriptor that we put into the set. For every file descriptor from 0 all the way up to that number, we emit the file descriptor and we say whether it's in the read set by emitting an R, or if it's in the write set by emitting a write character. And then if the PTO is not equal to null, that means that we had time remaining. And we report that remaining time and we exit. Okay. So now we'll see a little demo in the text of how to run that program. So we say in the following shell session log, we demonstrate the use of the program in listing 63.1. In the first example, we make a request to monitor file descriptor 0 for input with a 10-second timeout. Okay. T-select 10 second timeout. File descriptor 0 we want to read. Monitor for reading. Okay. We press enter so that a line of input is available on file descriptor 0. It then shows up as ready 1 and 0 is reported as ready. And then the timeout remaining was 8 seconds because it took them 2 seconds to hit enter. The above output shows that select determined that one file descriptor was ready. This was file descriptor 0, which is ready for reading. We can also see that the timeout was modified. The final line of output consisting of just the shell $ prompt appeared because the tselect program didn't read the new line character that made the file descriptor 0 ready. And so that character was read by the shell, which responded by printing another prompt. Well, that's interesting. Because we report whether it's ready, but we don't actually perform the read. And then we exit, and then something else performs a read. The above output shows us that select determined that one file descriptor was ready. Yeah. Okay, we already read that. In the next example, we again monitor file descriptor 0 for input, but this time with a timeout of 0 seconds. So that means it blocks forever. The select call return. Wait a minute. Sorry, if it's 0, it returns immediately. If it's null, it blocks forever. The select call returned immediately and found no file descriptor was ready. In the next example, we monitor 2 file descriptors. Descriptor 0 to see if input is available and descriptor 1 to see if output is possible. In this case, we specify input as available. Input is available. Sorry, my mind was wandering there. In the next example, we monitor 2 file descriptors, descriptor 0 to see if input is available, and descriptor 1 to see if output is possible. In this case, we specify the timeout is null, which is blocked forever. The first command line argument is a hyphen, meaning indefinitely. So it's going to unblock immediately because file descriptor 1 is always available for writing, or yeah, pretty much always available, unless the terminal buffers are full, which rarely happens. The select call returned immediately, informing us that the output was possible on the file descriptor 1. Next. Okay, so that was all select. That was pretty straightforward, very similar to Go select, with some, some weird APIs, but yeah, very very similar. The thing that I don't like is that like it's an ugly API. Let's go back to the prototype. Where is it here? So the select returns to you how many file descriptors are ready, but you don't know which sets they're in. So you have to iterate over all the sets. And you actually have to iterate over all the file descriptors because there's no way to iterate the sets. You could test to see if something is in a set, but you can't iterate over the members of a set. So really what you say when you call select is first you have to pass in the number of file descriptor, or the maximum numbered file descriptor, and then later you have to use that to iterate over all the file descriptors, testing to see if they have if they're members of the set. Which, I mean, set membership isn't a huge cost, doing all those checks, but it's also less than optimal if you just iterate it over the elements. So that's a bit of a weird thing. The timeout inconsistencies around the timeout behavior and the personalities, that's a weird thing. Yeah, I mean, it's not a horrible API, but it's pretty ugly. Okay, so now we're going to the poll system call. The poll system call performs a similar task to select. The major difference between the two system calls lies in how we specify the file descriptors to be monitored. With select, we provided 3 sets, each marked to indicate the file descriptors of interest. With poll, we provided a list of file descriptors, each marked with the set of events of interest. So in this case, we have a struct poll file descriptor, and we basically pass in a pointer to where in memory where those file descriptors are stored, and then we say how many there are in that array, and we have a timeout. I like this API a little bit better. And then int is maybe just errors. I wonder if pollFD is mutated. The pollFD array FDs and the NFDs argument specifies the file descriptors that poll is to monitor. The timeout argument can be used to set an upper limit on the time for which poll will block. We describe each of these arguments in detail below. So this is a simpler interface. It uses arrays instead of sets, which is nice. I prefer an array over a set. It's missing the except thing and distinctions between read and writing. So yeah, there's some differences there, but it's definitely simpler. So the pollFD array, the FD's argument lists the file descriptors to be monitored by poll. This argument is an array of pollFD structures defined as follows. Struct pollFD, which has the file descriptor as its first field, and then the requested events and a bit mask, and the returned events. Okay, so this will modify the R events field at the very least. The NFD's argument specifies the number of items in the FD's array. The NFD's T data type used to type the NFD's argument is an unsigned integer type. The events and R events field of the pollFD structure are bit masks. The caller initializes events to specify the events to be monitored for the file descriptor FD. Upon return from poll, R events is set to indicate which of those events actually occurred for this file descriptor. Table 63.2 lists the bits that may appear in the events and R events fields. The first group of bits in the table pull in read normal, read band, priority, read hup are concerned with input events. The next group of bits, out, write norm, write band are connected with output events. Third group of bits, pull error, hup, and endval are set in the R events field to return additional information about the file descriptor. If specified in the events field, these bits are ignored. The final bit, message, is used by poll on Linux. A Unix implementation providing streams devices, poll message indicates that a message containing a sigpoll signal has reached the head of the stream. Poll message is unused on Linux because Linux doesn't implement streams. That's good. Less shit in the kernel, the better. Alright, so this is what, a subsection 63.2.2. Okay, so we got 2 pages of text here, and then about a page of code. If events is specified as 0, the only bits that can be returned in R events are polar, poll hup, and poll endval. Specify a negative value for the FD field, e.g. negating its value if non-zero causes the corresponding events field to be ignored, and the R events field always to be returned as 0. This technique can be used to perhaps temporarily disable monitoring of a single file descriptor without needing to rebuild the entire FD's list. Although defined as separate bits, poll_in and poll_read norm are synonymous. Same thing with the right end. Poll_read band. So let's go through and read the description of these bits. So data other than high priority data can be read, equivalent to poll_in. Priority data can be read, which is unused on Linux, the out of band shit. High priority data can be read. Shutdown on per socket. Normal data can be written. Priority data can be written. And then return with our events is an error occurred, hangup occurred, file descriptor is not open. So poll_end val is invalid. And then message is unused on Linux. Okay. Poll_rd band is generally unused. That is, it is ignored in the events field and not set in our events. I love that Linux just chooses not to implement shit. I imagine most of these operating systems do the same thing. But like, I don't know. It's funny. Oh, they're just like, yeah, we're not going to do that. Poll_rd band is generally unused. That is, it's ignored in the events field and not set in our events. The only place where poll_rd band is set in code implementation, the obsolete DECnet networking protocol. Great. Although set for sockets in certain situations, poll_write band conveys no useful information. There's no circumstance in which poll_write band is set when poll_out and poll_norm are not also set. Poll_read band and poll_write band are meaningful in implementations that provide systems view streams, which Linux is not. Under streams, a message can be assigned a non-zero priority, and such messages are queued to the receiver in decreasing order of priority in a band ahead of normal priority 0 messages. Yeah, it seems like a lot of this stuff that's in the kernel, like, I could see why the kernel doesn't want to support it, because it's like, you can just do that in user space, bro. Like, if you really want it, do it in user space. And then, if you really need to be in the kernel, write a kernel module, or write a BPF program or something. Like, it's not up to the Linux kernel to do everything under the sun, you know. The X open source feature test macro must be defined in order to obtain the definitions of the constants poll. Okay, whatever. There's a bunch of stuff I do not care about. I just want to see an example. Poll_read hup is a Linux specific flag available since kernel 2.6.17 in order to obtain this definition from poll_h. The GNU source feature test macro must be defined. Poll invalid is returned if the specified file descriptor was closed at the time of the poll call. Summarizing the above points, the poll flags of real interest are poll_in, poll_out, poll priority, poll_read hup, poll hup, and poll error. We consider the meanings of these flags in greater detail in section 63.2.3. Okay. The timeout argument. The timeout argument describes the blocking behavior of poll as follows. If timeout equals -1, block until one of the file descriptors listed in the FD's array is ready, as defined in the corresponding. So that's kind of like null. Timeout for select. Timeout is 0, do not block. Just perform a check to see which file descriptors are ready. If timeout is greater than 0, block for that timeout milliseconds until one of the file descriptors FD is ready. or until a signal is caught. As with select accuracy of timeout is limited to the granularity of the software clock, and substitute theory specifies that timeout is always rounded upward if it is not an exact multiple of the clock granularity. Return value from poll. As its function result, poll returns one of the following. A return value of -1 indicates that an error occurred. One possible error is enter, indicating that the call was interrupted by a signal handler. As noted in section 21.5, poll is never automatically restarted if interrupted by a signal handler. A return of 0 means that the call timed out before any file descriptors became ready. A positive return value indicates that one or more file descriptors are ready. Return value is a number of poll FD structures in the FD's array that have a non-zero arguments field. Note the slightly different meaning of a positive return value from select and poll. The select system call counts the file descriptors multiple times if it occurs in more than one return file descriptor set. The poll system call returns a count of ready file descriptors, and a file descriptor is counted only once, even if multiple bits are set in the corresponding arguments field. I wonder if you have multiple elements for the same file descriptor, what would happen there? Example program listing 63.2 provides a simple demonstration of the use of poll. This program creates a number of pipes. Each pipe uses a consecutive pair of file descriptors, writes bytes to the right end of randomly selected pipes, and then performs a poll to see which pipes have data available for reading. Following shell session shows an example of what we see when running this program. The command line arguments to the program specifies that 10 pipes should be created, and writes should be made to 3 randomly selected pipes. Says write, poll returned with 2. Would have thought, okay, so the write went to the same file descriptor. And then readable is 3. Readable is 13. Oh, because those are the pairs. Yeah, the opposite pairs of the pipe. The read sides. From the above output, we can see that poll found 2 pipes had data available for reading. This is our main. I'm going to go through, oops, I'm on the wrong page here. So I'm going to read through the source code here. So getting past all the argument parsing. So the first thing we do, since the pipe number is 10, it means we like 2 times num pipes for the file descriptors, right? So PFDs, calc, the num pipes, size of, oh no, but it doesn't end 2 here. And then poll FDs is calc, same thing, but with a poll FD structure. And then we iterate over num pipes, we create our pipes, so we assign them into the pipe FDs. And then to figure out the number of writers, then we just parse that out from an argument. And then we go into our loop over our number of writers. We select a random pipe. We say, hey, we're writing to it. And then we perform our write. And then we go through, we create our poll FDs from our PFDs. And then we say the events that we're interested in is reading only. And then we do our poll, giving it the poll FD, which if we go up here is a pointer. Yep. And then the number of pipes, and then -1 to make it to where it is non-blocking. And then that gives us back how many are ready. Should be 2. And then here we go through each of our pipes and say, hey, if the pull FDJ are events and pull in says the returned events, then we say, hey, it's readable. Okay, so that's that section. So when is a file descriptor ready? Correctly using select and pull requires, so in my mind, select and pull are very similar APIs. Pull is a little bit simpler and easier to work with, but they both do essentially the same thing. It's probably just a historical Unix battle why there's 2 different methods of doing the same thing. Correctly using select and pull requires an understanding of the conditions under which a file descriptor indicates as being ready. Susty 3 says that a file descriptor with O non-block clear is considered to be ready if a call to an IO function would not block, regardless of whether the function would actually transfer data. The key point is italicized. Select and pull tell us whether an IO operation would not block, rather than whether it would successfully transfer data. In this light, let us consider how these system calls operate for different types of file descriptors. We show this information in tables containing 2 columns. Okay. The select column indicates whether a file descriptor is marked as readable, writable, or having an exceptional condition. The pull column indicates the bits returned in the R-events field. In these tables, we omit mention of pull RD norm, pull write norm, pull read band, and pull write band. Although some of these flags may be returned in R-events in various circumstances, if they are specified in events. They convey no useful information beyond that provided by pull in, pull out, pull up, and pull error. Okay. Regular files. File descriptors that refer to regular files are always marked as readable and writable by select and returned with pull in and pull out set in R events for pull. For the following reasons: a read will always immediately return data, end of file, or an error, e.g. the file is not open for reading. A write will always immediately transfer data or fail with some error. Susty 3 says that select should also mark a descriptor for a regular file as having an exceptional condition, though this is no obvious meaning for regular files. Only some implementations do this. Linux is one that does not. Okay. These are all different types of file descriptors. So terminals and pseudo-terminals. Table 63.3 summarizes the behavior of select and pull for terminals and pseudo-terminals. When one half of a pseudo-terminal pair is closed, the R events setting returned by pull for the other half of the pair depends on the implementation. On Linux, at least, the pull hub flag is set. However, other implementations return various flags to indicate this event. For example, pull hub, pull error, pull in. Furthermore, on some implementations, the flags that are set depend on whether it is the master or the slave device that is being monitored. So, condition or event. We got input available, output possible after close by pseudo terminal peer. Pseudo terminal master and packet mode detects slave state changes. Slave state change. Pipes and FIFOs. Okay. Okay. So all of this is when a file descriptor is, when is a file descriptor ready? think I might be sick with something. I don't know. I don't feel so bad that I'm like I am coughing and sneezing a lot, but I'm not, and I am congested, but not super congested. Maybe I am just sick. Maybe that's why I've been so like low energy the past like week, is I just had this like mild, mild sickness, mild cold. I mean, there's a lot of data points pointing to that I'm sick, but I just I haven't had a fever. I guess I could say that. Um, so that's good at least. All right. So pipes and FIFOs. Table 63.4 summarizes the details for the read end of the pipe or FIFO. The data in, what's that? Okay, it's this one. The data in pipe column indicates whether the pipe has at least one byte of data available for reading. In this table, we assume that pull in was specified in the events field for pull. On some other Unix implementations, if the right end of a pipe is closed, then instead of returning the pull hup set, pull returns with the pull in bit set, since a read will return immediately without a file. Portable applications should check to see whether this bit is set to in order to know if read will block. Table 63.5 summarizes the details for the right end of the pipe or FIFO. In this pipe, we assume that pull out was specified in the events field for pull. The space for pipe buff bytes column indicates whether the pipe has room to automatically write pipe buff bytes without blocking. This is the criterion on which Linux considers a pipe ready for writing. Some other Unix implementations use the same criterion. Others consider a pipe writable if even a single byte can be written. And earlier, the capacity of a pipe is the same as pipe buff. This means that pipe is considered writable if it contains even a single byte of data. Okay. On some other Unix implementations, if the read end of the pipe is closed, instead of returning the error set, pull returns whether either the pull out bit or the pull hup bit is set. Portable applications need to check to see if any of these bits is set to determine if a write will block. So select and pull indications for the read end of the pipe or FIFO. So if there's no data in the pipe and the right end is not closed, then pull says, hey, you're hanging up. Select says, yeah, go ahead and read. Sockets. Table 63.6 summarizes the behavior of select and pull for sockets. For the pull column, we assume that events was specified as pull in, pull out, pull priority. For the select column, we assume that the file descriptor is being tested to see if the input is possible, output is possible, or an exceptional condition occurred, i.e. the file descriptor is specified in all three sets passed to select. This table covers just the common cases, not all possible scenarios. The Linux pull behavior for Unix domain sockets after a peer close differs from that shown in table 63.6, as well as other flags. Pull additionally returns pull hup in our events. Select and pull indicates indications for sockets. Conditionary events, input available, read, output possible, write, incoming connection established from listening socket, read, out of band data, receive TCP only, X. That's the exceptional condition, which we don't really care about at all. and then stream socket peer closed connection. The Linux specific read hub flag needs a little further explanation. This flag actually is a form of epoll read hub. It's designed primarily for use when edge triggered mode of the epoll API. It is returned when the remote end of the socket stream connection has shut down the writing half of the connection. The use of this flag allows an application to use the epoll edge triggered interface to employ simpler code to recognize a remote shutdown. The alternative is for the application to know that the poll-in flag is set and then perform a read, which indicates the remote shutdown with a return of 0. Okay, so now we have our comparison, and then we're going to get into signal-driven I/O. Lots on signal-driven I/O. And then we get into epoll. Waiting on signals and file descriptors. I think there's like a signal FD thing. Gives you back a file descriptor. The pselect system call. Interesting. Then our summary. Okay. So you got lots to still read here. It's 10:30 already. So if I go here, I say man signal FD, I think it's called. Yeah. Alright, let's close up shop here. Comparison of select and poll. In this section, we consider some similarities and differences between select and poll. Implementation details. Within the Linux kernel, select and poll both employ the same set of kernel internal poll routines. These poll routines are distinct from the poll system call itself. Each routine returns information about the readiness of a single file descriptor. This readiness information takes the form of a bit mask whose values correspond to the bits returned in the R-events field by the poll system call. The implementation of the poll system call involves calling the kernel poll routine for each file descriptor and placing the result information in the corresponding R-events field. To implement select, a set of macros is used to convert the information returned by the kernel poll routines into the corresponding event types returned by select. These macros definitions reveal the semantic correspondence between the information returned by select and poll. If we look at select and poll columns in the tables in section 63.2, we see that the indication provided by each system call are consistent with the above macros. The only additional information we need to complete the picture is that poll returns poll invalid in the R-events field if one of the monitor file descriptors was closed at the time of the call, while select returns -1 with error no to ebad file descriptor. API differences. The following are some differences between the select and poll APIs. The use of fdset data type places an upper limit fdset size on the range of file descriptors that can be monitored by select. By definition, the limit is 1024 on Linux, and changing it requires recompiling the application. By contrast, poll places no intrinsic limit on the range of file descriptors that can be monitored. Because the FD set arguments of select are value result, we must reinitialize them if making repeated select calls from within a loop. By using separate events inputs in our events output fields, poll avoids this requirement. The timeout precision afforded by select is greater than that afforded by poll. Yeah, I saw that. Microseconds versus milliseconds. The accuracy of the timeouts of both of these system calls is nevertheless limited by the software clock granularity. If one of the file descriptors is being monitored was closed, then poll informs us exactly which one via the poll enval bit in the corresponding R events field. By contrast, select merely returns -1 with error no set to bad file, leaving us to determine which file descriptor is closed by checking for an error when performing an IO system call on the descriptor. However, this is typically not an important difference since an application can usually keep track of which file descriptor has closed. Portability. Historically, select was more widely available than poll. Nowadays, both interfaces are standardized by SUSV 3 and widely available on contemporary implementations. However, there is some variations in behavior of poll across implementations, as noted in section 63.2.3. Performance. The performance of poll and select is similar if either of the following is true. The range of file descriptors to be monitored is small, i.e. the maximum file descriptor number is low. A large number of file descriptors are being monitored, but they are densely packed, i.e. most of the file descriptors from 0 up to the limit are being monitored. However, the performance of select and poll can differ noticeably if the set of file descriptors to be monitored is sparse. That is, the maximum file descriptor number n is large, but only one or a few descriptors in the range 0 to n are being monitored. In this case, poll can perform better than select. We can understand the reasons for this by considering the arguments passed to the two system calls. With select, we pass one or more file descriptors sets and an integer NFDs, which is one greater than the maximum file descriptor to be examined in each set. The NFD's argument has the same value regardless of whether we are monitoring all file descriptors in the range or only the descriptor NFDs minus 1. In both cases, the kernel must examine NFD's elements in each set in order to check exactly which file descriptors are to be monitored. By contrast, when using poll, we specify only the file descriptors of interest to us, and the kernel checks only those descriptors. The difference in performance for poll and select with sparse descriptor sets was quite significant in Linux 2.4. Some optimizations in Linux 2.6 have narrowed the performance gap considerably. We consider the performance of select and poll further in section 63.4.5, where we compare the performance of these system calls against epoll. Boop. Problems with select and poll. The select and poll system calls are the portable, long-standing, and widely used methods of monitoring multiple file descriptors for readiness. However, these APIs suffer some problems when monitoring a large number of file descriptors. On each call to select or poll, the kernel must check all of the specified file descriptors to see if they are ready. When monitoring a large number of file descriptors that are in a densely packed range, the time required for this operation greatly outweighs the time required for the next two operations. In each call to select or poll, the program must pass a data structure to the kernel describing all the file descriptors to be monitored. And after checking the descriptors, the kernel returns. I don't know what epoll's interface looks like. I'm kind of curious what it's going to look like at the end here. Signal-driven I/O just seems like a freaking nightmare. I would never want to do that. Signals are a complete nightmare. So I don't see how signal-driven I/O is going to be a good thing. But to get back to epoll, I don't know what the interface looks like, but the thing that I'm interested in is like just giving the file descriptors as integers to the kernel, and then saying, give me one file descriptor from that that I can take an action on. Since it's operating in a single threaded loop, I don't need to know all of the file descriptors that are available. I mean, that might be helpful to reduce system call overhead, but even just give me back the one random one, like Go does. Like Go's select statement, only one case will actually execute, even if multiple cases are available to execute. So it'd be nice if you say, here's a bunch of file descriptors that I want to potentially block on for a certain period of time to wait for them to be available. And just tell me which ones are available. And the interface to that would be like an array of integers, the length of the array, and maybe a location in memory. If you don't want to take an allocation, maybe a location in memory and a length to write the results into. That would be like a super simple interface that I could get on board with, but I don't think epoll is going to be simple. All right, let's continue reading. Where do we leave off here? After the call to select or pull, program must inspect every element of the return data structure to see if which file descriptors are ready. The consequence of the above points is that the CPU time required by select and pull increases with the number of file descriptors being monitored. This causes problems for programs that monitor large numbers of file descriptors. The poor scaling performance of select and pull stems from a simple limitation of these APIs. Typically, a program makes repeated calls to monitor the same set of file descriptors. However, the kernel doesn't remember the list of file descriptors to be monitored between successive calls. Signal-driven I/O and epoll, which we just examined in the following sections, are both mechanisms that allow the kernel to record a persistent list of file descriptors in which the process is interested. Doing this eliminates the performance scaling problems of select and pull, yielding solutions that scale according to the number of I/O events that occur, rather than according to the number of file descriptors being monitored. Consequently, signal-driven I/O and epoll provide superior performance when monitoring large number of file descriptors. Okay. Let's see how many pages of signal-driven I/O stuff we got. Let's see, 1.5. And we got 1.5 pages of code. 2.5. What's that? 3, 4, 5, 6, 7. So 7 pages of signal. I guess that isn't that bad. 7 pages and like a page and a half of code. Just to touch base on this topic. I'm not interested in actually using it. Okay, we've been going for an hour and a half. So I'm going to go for at least another half hour here. Signal-driven I/O. With I/O multiplexing, a process makes a system call select or pull in order to check whether I/O is possible on a file descriptor. With signal-driven I/O, a process requests that the kernel send it a signal when I/O is possible on a file descriptor. The process can then perform any other activity until I/O is possible, at which time the signal is delivered to the process. To use signal-driven I/O, the program performs the following steps. 1. Establish a handler for the signal delivered by the signal-driven I/O mechanism. By default, this notification signal is sig.io. Select the owner. Sig.io, what is... There we go. Sig.io. So that's a standard signal. That's SIG IoT though. We're looking for SIG IO, which is not standard. It's a, well, no, that is a standard signal. Thought maybe it was real time. So standard signals, I don't think you communicate additional information. I think it requires real-time signals. So the important thing here is that you can send additional information with standard signals, but they're not queued, they're coalesced. So you're going to lose information if multiple signals of the same type are sent. So we'll see if they use that mechanism or not. All right. Set the owner of the file descriptor, that is the process group, that is to receive signals when I/O is possible on the file descriptor. Typically, we make the calling process the owner. Owner is set using an FCNTL set own operation, the following form. Enable non-blocking I/O by setting the O non-block open file status flag. Enable signal-driven I/O by turning on the O async open file status flag. This can be combined with the previous steps since they both require the use of the FCNTL setFL operation. As in the following example. The calling process can now perform other tasks. When I/O becomes possible, the kernel generates a signal for the process and invokes a signal handler. Signal-driven I/O provides edge-triggered notification. This means that once the process has been notified that I/O is possible, it should perform as much I/O, e.g. read as many bytes as possible, assuming a non-blocking file descriptor. This means executing a loop that performs I/O system calls until the call fails with error E again or E would block. On Linux 2.4 and earlier, signal-driven I/O can be employed with file descriptors for sockets, terminals, pseudo-terminals, and certain other types of devices. On Linux 2.6, additionally, it allows signal-driven I/O to be employed with pipes and FIFOs. Since Linux 2.6.2.5, signal-driven I/O can be used with iNotify file descriptors. On the following pages, we first present an example of the use of signal-driven I/O, and then explain some of the above steps in greater detail. Okay. Historically, signal-driven I/O was sometimes referred to as asynchronous I/O. And this is reflected in the name OAsync of the associated open file status flag. However, nowadays the term asynchronous I/O is used to refer to the type of functionality provided by POSIX AIO and IOU-ring. Using POSIX AIO, a process requests the kernel to perform an I/O operation, and the kernel initiates the operation, but immediately passes control back to the calling process. The process is then later notified when the I/O operation completes or an error occurs. OAsync was specified in POSIX 1G, but was not included in SUSV 3 because the specification of the required behavior for this flag was deemed insufficient. Several Unix implementations, especially older ones, don't define the OAsync constant for use with FCNTL. Instead, the constant is named f_async, and glibc defines the latter name as a synonym for o_async. Boop. Let's get into it. Listing 63.3 provides a simple example of the use of signal-driven I/O. This program performs the steps described above for enabling signal-driven I/O on standard input. And then places the terminal in C-break mode. C-break, what is that? That was like a terminal thing. Place the terminal in C-break mode so that input is available a character at a time. The program then enters an infinite loop, performing the work of incrementing the variable C and T while waiting for the input to become available. Whether input becomes available, the SIG.IO handler sets a flag .SIG.IO that is monitored by the main program. When the main program sees that this flag is set, it reads all available input characters and prints them along with the current value of count. If a hash character is read in the input, the program terminates. Here's an example of what we see when we run the program and type the X character a number of times, followed by a hash character. Okay. Okay. Let's go over the program. Okay, so they made the got SIG.IO a volatile SIG atomic T. I've been using the underscore atomic thing because ChatGPT told me that was like the best way of doing it. So the handler basically just sets that flag. And then we have our main here, which sets our signal handler. And then we set our ownership for standard in to be the process, the current process, so that we get the signals. And then we set it to be an o_async and o_non-block mode. O_async is signal-driven I/O, and o_non-block is just a not block on I/O operations. And then we set C-break mode, so we get characters at a time instead of lines at a time. And then we go into our loop. We say initially done is equal to false. Our count is equal to 0. And our count is equal to 0. So that's our initialization. Then we say as long as we're not done, we're going to count plus plus on the loop. So the count is just a loop count. We use a hot loop inside that to slow down the main loop a little bit. We check to see if we got signal I/O. And we can do that because it's a volatile SIG atomic type. If we read that value, then we can assign to got SIG.IO the value 0. Read all available input until error, probably E again. Yep. Or EOF. Or hash character is read. Okay. So we do our read one character at a time into the CH buffer, which is indeed a character. So while it's not done, and our read is actually returning bytes, then we print out the count, the read, and then we set done. So basically we hit 0, the read, which isn't EOF. Is that EOF? Oh, basically this got will block. How do we get out of this though? Because we're not going to be setting done, so we can exclude that. So that means our read must be, oh, it's going to be returning negative value here with like a E again. Yeah, that's what it says, probably E again here. Okay. And then restore at terminal settings, and we exit. Okay. Okay. Maybe we get through the rest of signal-driven I/O reading, and then I will take a break at ePoll, and then after lunch, come back, do the reading on ePoll. And then there's a section on waiting on signals and file descriptors, and then summary. So it's mostly ePoll for the rest of the. Okay, let's get through the rest of signal I/O, and then I'll take a break for lunch. It looks kind of overcast out today, so I don't know, maybe I'll take a walk. All right. Establish a signal handler before enabling signal-driven I/O. Makes sense. Because the default action of SIG-IO is to terminate the process, we should enable the handler for SIG-IO before enabling signal-driven I/O on the file descriptor. If we enable signal-driven I/O before establishing the SIG-IO handler, then there's a time window during which, if I/O becomes possible, delivery of SIG-IO will terminate the process. On some Unix implementations, SIG-IO is ignored by default. Setting the file descriptor owner. We set the file descriptor owner using an fcntl operation for the following form. We may specify that either a single process or all the processes in a process group are to be signaled with I/O as possible on the file descriptor. If PID is positive, it is interpreted as a process ID. PID is negative, its absolute value specifies a process group ID. In older Unix implementations, an ioctl operation, either FIO set-own or SIOS/RCSP group, was used to achieve the same effect as set-own. For compatibility, these ioctl operations are also provided on Linux. Typically, PID is specified as a process ID of the calling process so that the signal is sent to the process that has the file descriptor open. However, it's possible to specify another process or a process group, e.g. the caller's process group, and signals will be sent to that target subject to the permission checks described in section 25, where the sending process is considered to be the process that does the fsetOwn. The fcntl getOwn operation returns the ID of the process or process group that is to receive signals when I/O is possible on the specified file descriptor. So fcntl getOwn gives back the PID. We say, hey, if it's -1, we exit. A process group ID is returned as a negative number by this call. The ioctl operation that corresponds to fgetOwn on older Unix implementations was FIO getOwn or S. Yeah, okay. Just compatibility stuff with ioctl. A limitation in the system call convention employed on some Linux architectures, notably x86, means that if a file descriptor is owned by a process group less than 4096, then instead of returning that ID as a negative function result from the fcntl getOwn operation, glibc misinterprets it as a system call error. Consequently, the FCNTL wrapper function returns -1. An error node contains a positive process group ID. This is a consequence of the fact that the kernel system call interface indicates errors by returning a negative error node value as a function result, and there are a few cases where it is necessary to distinguish such results from a successful call that returns a valid negative value. To make this distinction, glibc interprets negative system call returns in the range of -1 to -495 as indicating an error, copies this absolute into error node and returns -1 as a function result for the application program. This technique is generally sufficient for dealing with a few system call service routines that can return a valid negative result. The FCNTL get-own operation is the only practical case where this fails. This limitation means that an application that uses process groups to receive I/O possible signals, which is unusual, can't reliably use get-own to discover the process group owns a file descriptor. Since glibc version 2.11, the FCNTL wrapper function fixes the problem of fgetOwn, which process group ID is less than 4096. It does this by implementing fgetOwn in user space using the fgetOwnX operation, which is provided by Linux 2632 and later. Okay. When does I/O possible signal? Okay, got four more pages here. We now consider details of when I/O possible is signaled for various file types, terminals and pseudo-terminals. For terminals and pseudo-terminals, a signal is generated whenever new input becomes available, even if process input is not yet read. Input possible is also signaled if an end-of-file condition occurs on terminal, but not a pseudo-terminal. There are no output possible signals for terminals. A terminal disconnect is also not signaled. Starting with kernel 2.4.19, Linux provides output possible signaling for the slave side of the pseudo-terminal. This signal is generated whenever input is consumed on the master side of the pseudo-terminal. Pipes and FIFOs. For the read end of a pipe or FIFO, a signal is generated. In these circumstances, data is written to the pipe, even if it was already unread input available. Right end of the pipe is closed. For the right end of the pipe of FIFO, a signal is generated in these circumstances. A read from the pipe increases the amount of free space in the pipe so that it is now possible to write pipe buff bytes without blocking. The read end of the pipe is closed. Socket signal-driven I/O for datagram sockets in both Unix and Internet domains. A signal is generated in the following circumstances. An input datagram arrives on the socket, even if there were already unread datagrams waiting to be read. An asynchronous error occurs on the socket. Signal-driven I/O works for stream sockets in both the Unix and the Internet domains. A signal is generated in the following circumstances. A new connection is received on a listening socket. A TCP connect request completes. That is, the active end of the TCP connection entered the established state, as shown in the figure 61.5. The analogous condition is not signaled for the Unix domain sockets. A new input is received on the socket even if there was already unread input available. The peer closes its right half of the connection using shutdown or closes its socket altogether using close. Output is possible on the socket, e.g. space has become available in the socket send buffer. An asynchronous error occurs on the socket. iNotify file descriptors. A signal is generated when the iNotify file descriptor becomes readable. That is, an event occurs for one of the files monitored by iNotify file descriptor. Refining the use of signal-driven I/O. In applications that need to simultaneously monitor very large numbers, thousands of file descriptors, for example, certain types of network service, signal-driven I/O can provide sufficient performance advantages. By comparison with select and pull, signal-driven I/O offers superior performance because the kernel remembers the list of file descriptors to be monitored and signals the program only when I/O events actually occur on those descriptors. As a result, the performance of the program employing signal-driven I/O scales according to the number of I/O events that occur, rather than the number of file descriptors being monitored. To take full advantage of signal-driven I/O, we must perform two steps: employ lane-specific FCNTL operation set sig to specify real-time signal that should be delivered instead of sig I/O when I/O is possible on a file descriptor. Specify the SA sig info flag when using sig action to establish a handler for the real-time signal employed by the previous step. That's what I was getting at. Like real-time signals, you need to do a little bit more work to get the sig info, additional info. The FCNTL set sig operation specifies an alternative signal that should be delivered instead of sig IO when IO is possible on a file descriptor. The F get sig operation performs the converse of set sig, retrieving the signal currently set for the file descriptor. Okay, so you can say, hey, for these specific file descriptors, we're going to have a different signal come in other than sig IO. Make sense? In order to obtain the definitions of the F set sig, sorry, I'm on the wrong page here. Wait a minute. Oh, no, that's the right page. In order to obtain the definitions of the F set sig and F get sig constants from FCNTL, we must define the GNU source feature test macro. If F set sig, using F set sig to change the signal used for IO possible notification serves two purposes, both of which are needed if we are monitoring large numbers of IO events on multiple file descriptors. The default IO possible signal, sig IO, is one of the standard non-queuing signals. If multiple IO events are signaled while sig IO is blocked, perhaps because the sig IO handler is already invoked, all notifications kept at first will be lost. If we use set sig to specify a real-time signal as the IO possible signal, multiple notifications can be queued. If the handler of the set signal is established using sig action call in which the sig info flag is specified in the SA flags field, then sig info T structure is passed as the second argument to the signal handler. This structure contains fields identifying the file descriptor on which the event occurred, as well as the type of event. Note that we use both set sig and sig info. Note that the use of both set sig and sig info is required in order for a valid sig info T structure to be passed to the signal handler. If we perform an set sig operation specifying sig as 0, then we return to the default behavior, sig IO is delivered, and the sig info T argument is not supplied to the handler. For an IO possible event, the fields of interest in the sig info T structure pass to the signal handler as follows: the sig node, the number of signal that caused the invocation of the handler. This value is the same as the first argument of the signal handler. FD, the file descriptor for which the IO event occurred. Code indicating a type of event that occurred. Value that can be appeared in this field along with their general descriptions is shown in a table of 63.7. Band, a bit mask containing the same bits that are returned in the R events field by the poll system call. The value set in SI code has a one-to-one correspondence with the bit mask set in SI band as shown in table 63.7. Table 63.7, SI code and SI band values in the sig info T structure for IO possible events. Makes sense? In an application that is purely input driven, we can further refine the use of set sig instead of monitoring IO events via a signal handler. We can block the nominated IO possible signal and then accept the queued signals via calls to sig wait info or sig time the wait. These system calls return a sig info T structure that contains the same information as is passed the signal handler established with SA sig info. Accepting signals in this manner returns us to a synchronous model of event processing, but with the advantage that we are much more efficiently notified about file descriptors on which IO events have occurred than if we use select or poll. So that's basically saying like, hey, you can use sig wait info or sig time to wait to get the SA info back. Instead of using the signal handler. Handling signal queue overflow, which is bound to happen. We saw in section 22.8 that there is a limit on the number of real-time signals that may be queued. If this limit is reached, the kernel reverts to delivering the default SIG-IO signal for IO possible notifications. This informs the process that a signal queue overflow occurred. When this happens, we lose information about which file descriptors have IO events because SIG-IO is not queued. Furthermore, the SIG-IO handler doesn't receive a SIG info T argument, which means that the signal handler can't determine the file descriptor that generated the signal. We can reduce the likelihood of signal queue overflows by increasing the limit on the number of real-time signals that can be queued, as described in section 22.8. However, this doesn't eliminate the need to handle the possibility of an overflow. A properly designed application using setSig to establish real-time signal as the IO possible notification mechanism must also establish a handler for SIG-IO. If SIG-IO is delivered, then the application can drain the queue of real-time signals using SIG-WAIT-INFO and temporarily revert to the use of select or poll to obtain a complete list of file descriptors with outstanding IO events. Using signal-driven IO with multi-threaded applications. Starting with kernel 2.6.32, Linux provides two new non-standard fcntl operations that can be used to set the target for IO possible signals, fsetOwnEx and fgetOwnEx. The fsetOwnEx operation is like fsetown, but as well as allowing a target to be specified as a process or process group, it also permits a thread to be specified as a target for IO possible signals. Okay. For this operation, a third argument of fcntl is a pointer to the structure of the form of type and PID. The type of the field defines the meaning of the PID field as one of the following values: owner group, owner PID, TID. If the getOwnX operation the getOwnX operation is the converse of the setOwnX operation. It uses to get the it uses the owner EX structure pointed to by the third argument fcntl to return the settings defined by the previous setOwnEx operation. Because the setOwnEx and getOwnEx operations request process group IDs as positive values, the getOwnEx doesn't suffer the problems described earlier for getOwn when using the process group IDs less than 4096. Yeah. Okay. It still uses just regular signals. Yeah. Okay. So now we're at the ePOL API section, and it is 2 hours and 7 minutes of streaming. So I'm going to call it here, grab some lunch, and be back in a couple of hours. Cool. And then we'll dive into ePOL. And ePOL will take us all the way to a section on waiting on signals and file descriptors, and then that's it. So it's pretty much just ePOL remaining. I guess to kind of like take a step back and just digest what we just read. So we covered select and poll. The select and poll, they both have kind of similar portability as far as like support. Select API, I didn't like it because it uses these set data structures and required you to iterate over like a huge range of file descriptors. It's just kind of gross. I didn't like the API. Poll I liked a little bit more because it was an array of signals that you're interested in. And you can just iterate over the array and see what happened, what actions happened or whatever. So I like that one a little bit better. Just the API just seemed a little bit nicer to use. But both select and poll suffer from the disadvantage of not being able to scale to large numbers of file descriptors because their cost scales linearly with the number of file descriptors being monitored. So then we can go into signal IO, which solves that problem. But the problem with signal IO is that it's signal driven. So you have all the complexities of signals. So the first thing to do is to replace the default signal with a real-time signal so that you can get the SIG-info structure passed into your signal handler, and then also switch from using a signal handler to a dedicated thread that's waiting for these SIG-info actions. And then you have to consider the inevitability that your signals, your queue of signal IO event signals might fill up, in which case the kernel is going to revert to using the non-real-time signal, and you need to be able to handle that situation, which would be to drain the queue and fall back to using select and pull to complete a bunch of IO operations and then go back to doing signal-based IO. So it doesn't prevent you from from the requirement of using select and pull, but it does scale a little bit better, and it also introduces a lot of complexity in just like dealing with signals. So I don't like signals either. The signal-based IO, even if you can get more performance and scalability, I should say, with a large number of file descriptors, given these like weird edge cases that you have to handle and how it kind of like behaves in those edge cases, like I'd rather just avoid all that complexity. So hopefully the ePOL API gives us the scalability that we want without the downside of having to use signals and all the complexity involved with that. So that's where we're at. I'm going to leave it there. I'll be back in a couple hours here to resume on ePOL. Cool. All right. Have a good one. Bye.